My video project will be about a previous project I have done regarding my design for an electrical bike generator. I've had this idea of an electrical bike for quite some time, mainly as a fantasy as I ride my bike every day through the rain and mud. uh, it should be noted that I came up with this design halfway through the semester. Had I known more about circuit design, I would have certainly built it differently. However, this is a good design for the sake of displaying how many of the design concepts that I've learned early on this semester can be applied together to create something very useful for our daily lives. The design for the electrical bike generator has several functions and variables in the circuit design. The first one is the power switch that ultimately turns the generator on, permitting usage of the device. When the power button is on, a small light bulb is lit up to indicate the device is in use. Another occurrence is that the pedals are separated or unlocked from the gears. I want a mode where you can ride the bike normally because there should always be an alternative if your bike generator breaks or shuts down. I am certain there is a much more efficient way to switch between these modes, but this is what I came up with. So the pedals are unlocked in such a way that when the electrical bike is in use, the pedals will not be in the way when the gears are moved by the motor. When the motor is off, the pedals are locked into gears so that the bike can be used when the motor is on. There are two toggle buttons that can be used when the device is on. They are the speed button and the brake button. The speed button allows the user to increase the speed of the bicycle by one speed level. The brake button decreases the speed by one speed level. There are 8 speed levels. The initial one has no speed. Each level is an increment of 2.5 miles per hour. The maximum speed you can go on the electrical bike is 15 miles per hour. It should be noted that the power button can be used as a fail-safe if the user wants to stop the bike faster, since the user will be able to safely use the handbrakes when the generator is off. I might as well disregard handbrakes altogether, or at least disconnect the handbrakes when the electrical mode is on, since having those while the bike is running at a very high speed can be a huge safety hazard. The speed of the bicycle is primarily determined on how the variation of the speed and the brake buttons are used. The most important variation in the design are the adder subtractor and the carry input. Both variables are placed in a 3-bit full adder to determine what speed level to use. If the speed button is used by itself, then the result of the add subtract input, B, is an adder with a magnitude of 1. If the brake button is used, then input B is a subtractor with a magnitude of 1. Since not only the B input is on, but the carry input, C1, is as well. If both buttons were to be simultaneously pressed at the same time, the speed does not change. Once the inputs for the full adder is set up, then the level of the speed is calculated. The full adder adds or subtracts inputs B and A, with input A initially at 0. From the brake button, the full adder subtracts by 1 with the carry input and the add subtract input high. From the speed button, the full adder adds by 1 with the add subtract input high. The carry output C and the sum output S of input B and input A are transferred in a D flip-flop. The D flip-flop stores the sum output into input A so that the bicycle stays at that speed until a button is pressed, altering the speed once again. The summation output also takes effect in 2 or more of the design circuits. The output is stored in the BCD to 7-segment decoder. For those who are not familiar with this type of decoder, it converts the output into a code used for a 7-segment display. The 7-segment display is used to tell the user what speed level the user is on by displaying a numerical value that the level represents. This 7-segment decoder and a 7-segment display were used in one of our labs earlier on this semester. The summation output is also stored in a 3x8 decoder. The purpose of the decoder is to convert the output values into an 8-bit value. This 8-bit value is transferred to the motor, being the final stage in moving the bicycle. The enable E serves as a fail-safe connected directly to the power input. If the power is off, then the decoder is no longer enabled, and thus the motor is stopped. One more concept that needs to be addressed are some of the assumptions for the circuit. The most important assumption is that there are no gate delays. Typically, many realistic designs have gate delays, but what I have created is an ideal model. Voltage will go through each gate equally for 1 nanosecond. Voltage is going through the circuit is also a very important part of the circuit, but how the voltage is implemented goes beyond my current academic knowledge, and even if I did know how to implement the voltage value so that my circuit does work correctly, I may just have to radically change my design from scratch. There are tons of considerations I would have to consider, like how much power will I need used to generate the bike wheel for each speed mode, so that way the bike moves at a certain rate. Another consideration is how to distribute different amounts of voltage such that all the correct amounts are used for every function of my design, and also to avoid breaking the circuit in the process, because that's very common if you don't use the values correctly. Nonetheless, this design is still a great way to show how we can apply what we learn to create something cool like an electrical bike generator. Personally, I enjoyed working on this design. I hope for those who are new to circuit design that you learned something new from this video.